A geomagnetic storm, often referred to as a magnetic storm, is a temporary disturbance of the Earth's magnetosphere caused by solar wind shock waves and/or cloud of magnetic field that interacts with the Earth's magnetic field. These storms can disrupt communication systems, navigation, and even power grids, making understanding their causes and effects crucial for both scientific research and practical applications. The Earth's magnetosphere. To comprehend geomagnetic storms, it's essential to first understand the Earth's magnetosphere. The magnetosphere is a region around the Earth dominated by the planet's magnetic field. It acts as a shield, protecting the Earth from the majority of the solar wind, which is a stream of charged particles emitted by the Sun. The magnetosphere is shaped by the interaction between the Earth's magnetic field and the solar wind, forming a teardrop-shaped region with a long tail extending away from the Sun. Solar activity in the Sun-Earth connection. The Sun is a highly dynamic star, exhibiting various forms of activity that influence space weather, including sunspots, solar flares, and coronal mass ejections, CMEs. These phenomena are critical in the context of geomagnetic storms. Sunspots, dark, cooler areas on the Sun's surface associated with intense magnetic activity. Sunspots can lead to solar flares and CMEs. Solar flares, sudden, intense bursts of radiation originating from the Sun's surface. While solar flares can affect the Earth's ionosphere and radio communications, they are not the primary cause of geomagnetic storms. Coronal mass ejections, CMEs, massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. When a CME is directed towards Earth, it can interact with the Earth's magnetosphere, leading to geomagnetic storms. The mechanics of a geomagnetic storm. A geomagnetic storm begins when a CME or high-speed solar wind stream reaches the Earth. The storm typically unfolds in 3 phases. Initial phase. The storm's onset is marked by a sudden increase in the solar wind pressure, causing a compression of the magnetosphere. This phase lasts for several hours. Main phase. The primary interaction between the solar wind and the magnetosphere occurs during this phase, leading to significant geomagnetic activity. This can last from several hours to days. Recovery phase. The magnetosphere gradually returns to its normal state, which can take several days. The interaction between the solar wind and the Earth's magnetosphere during the main phase involves complex processes, including magnetic reconnection, where the magnetic field lines from the solar wind merge with those of the Earth's magnetic field. This releases vast amounts of energy, injecting energetic particles into the Earth's magnetosphere and causing disturbances in the magnetic field. Effects of geomagnetic storms. Geomagnetic storms can have various impacts on both natural and technological systems. Auroras. One of the most visually stunning effects of geomagnetic storms is the enhancement of auroras, or northern and southern lights. These natural light displays occur when charged particles from the magnetosphere collide with atoms in the Earth's upper atmosphere, causing them to glow. Satellite operations. Satellites orbiting the Earth can be adversely affected by geomagnetic storms. Increased radiation can damage satellite electronics, interfere with communication signals, and even alter satellite orbits due to increased atmospheric drag. Communication systems. High-frequency radio waves, used for long-distance communication, can be disrupted during geomagnetic storms. This is particularly problematic for aviation and maritime navigation, which rely on these signals. Power grids. Geomagnetic storms can induce electric currents in power lines, potentially causing voltage instability, transformer damage, and in severe cases, widespread power outages. One notable example is the 1989 Quebec blackout, caused by a geomagnetic storm that left millions without power for several hours. Navigation systems. Geomagnetic storms can degrade the accuracy of GPS signals, impacting navigation systems used in aviation, maritime, and personal applications. Monitoring and predicting geomagnetic storms. Given the potential impacts of geomagnetic storms, monitoring and predicting these events is critical. Agencies like NASA, NOAA, and the European Space Agency, ESA, use a network of ground-based observatories and space-based satellites to monitor solar activity and the state of the Earth's magnetosphere. Instruments like magnetometers, solar telescopes, and space weather satellites provide real-time data to help predict geomagnetic storms. Predictive models rely on observations of solar activity, particularly the detection of CMEs, to forecast the arrival time and potential impact of geomagnetic storms. While prediction capabilities have improved, accurately forecasting the severity and precise impact remains a challenging task due to the complex nature of space weather interactions. Conclusion: geomagnetic storms are fascinating and powerful natural phenomena resulting from the dynamic interactions between the Sun and the Earth's magnetosphere. While they can create beautiful auroras, they also pose significant risks to modern technological systems. Understanding the causes, mechanics, and effects of geomagnetic storms is essential for mitigating their impacts and safeguarding our technological infrastructure. As our reliance on technology continues to grow, ongoing research and improved monitoring capabilities will be crucial in enhancing our ability to predict and respond to these cosmic events.